Okay, now I've gone ahead and written out the expression that we get. Let's just see what we do. We multiply both sides by sum of xi squared, so we're going to get an a sum of xi squared, and we're going to have that over on the left side. Then on the right side, we're going to have this numerator. We're going to want to multiply by n, which will put an n in front of this term and the term that we get here. And that's going to result in the expression that I can't really, maybe I can, yeah, I can show that. Okay, so multiplying through by sum of xi squared, we get a sum of xi squared. Then multiplying through by n, we get an na sum of xi squared. When we multiply through by the n, this term also gets multiplied by n, and then we're left with just this numerator. And that equation can be rewritten and solved for a just by adding this term to both sides. We get na sum of xi squared plus a times the sum of xi quantity squared equals n times the sum of xi yi hat minus the sum of xi yi. Now if I hadn't made any errors in signs and so forth, this should resolve pretty easily. We can factor a out of this side and then divide this side by what we get when we factor. I'm going to skip that step. This has already gone on long enough, and you should easily be able to understand this. So a is going to be this minus this divided by what we get when we factor a out of this term, which is going to be n times the sum of xi squared plus the sum of the xi quantities squared. Not completely unexpectedly, I appear to have a sign problem. I'm being careless with my algebra. We have a minus here, and that's going to have an effect. So we're going to correct that. Tracing the errors back, a minus 2 times a minus b is plus 2b, which will give us a plus 2b here. So that when we write down these equations, we're going to have a plus 2b here. This plus 2b changes our solution here, changes the signs of both of these terms. We have a negative here and a positive here. So we're going to have a negative here and a positive here. That results in a negative here, and I'm going to have to use some parentheses, and a positive here. And having changed the signs of these two terms, we're going to end up changing the signs of these two terms, except I made a mistake on the sign of this term, so that this becomes a plus, and this remains a minus. The net result being that this term here will be negative, this one remains negative, and the only difference in my final expression is that I'm going to have a negative here. I'm going to fix that off camera. Now we've got the changes. We have the minus here and the minus here. This is now the correct formula for A, and the formula for B, which we obtained here, was that B equals, we'll do sum of yi minus a times the sum of the xi divided by n. if I made that B look any better or not. So we can get our slope and our intercept of our best fit straight line. Remember, our premise was y equals ax plus b, and all we've done here is to minimize the sum of the squares of our differences between our observed y values and our predicted y values. Okay, so knowing all our xi's and yi hats, all our observed values of x and y, we can plug them into this formula. We also have to know our value of n, which is just how many data points we have, and we get our value for a. And then we can do the same thing. We can take our value of a along with our known values of yi hat and xi hat. Not sure where the yi's lost their hats, but they've all got hats. Looking back, the yi's appear to have lost their hats between writing down the equations and writing down our solution for b. These yi's all need hats, and I think that corrects it, and I've corrected it here. Okay, again, given our values of xi and yi hat, and there's another one without a hat. It might have been the one I noticed originally. Okay, now given our xi's and our yi hats, our observed values of x and y, we easily calculate a. I say easily. These are fairly straightforward sums. They're not difficult to calculate, especially if you have a spreadsheet. B then uses the value of a plus our observed values of xi's and yi hats, our observed x and y values, and we obtain the equation of the straight line that minimizes the squares of the vertical distances between the line and the points. Here is our set of equations. Now, the purpose of this exercise is not to give you an equation to plug into your calculator or whatever and get the right answer. It's to show you the process, because there are other situations in which you have to do similar optimizations for formulas that you might not have. For example, if we wanted to do a quadratic fit to our data points, we would minimize the distance between an ax squared plus bx plus c function and our point. Okay, there are formulas for that also, but you need to understand how the calculus works. Won't say that you necessarily need to in order to pass the course, but this is certainly a valid question. It could occur on a test. Whether it does or not is sort of up to chance. But the situation, to recapitulate, is simply we have data points, we have a line with variable parameters a and b, and we try to minimize the sum of the squares of the values predicted by the y equals ax plus b using the observed values of x and the actual observations, the yi hats that we've actually, the quantities, the yi hat quantities that we've actually observed. I'll just conclude this one by saying the devil is in the details, and you have ample proof of that here. You have to be very careful with signs, very careful to write things out correctly. So do as I say, not as you've seen me do.